All right, welcome back. So we want to continue talking about branch prediction. If you remember, we were talking about the fact that we want to do taken, right? And in order to predict taken, you need the next address in the fetch state, okay? And finding the next address in the fetch state is not something trivial, because when you're fetching an instruction, you have no idea what this instruction is. But now we are asking to know not only what instruction this is, but also knowing that if this is a branch, what is the target address? In other words, what is the PC plus offset? In order to do that, we came up with this idea that I don't need to decode the instruction. What I need to do is a mechanism where I remember the past events. So whenever I see a branch, I also record the target branch of that. And there will be a table where I'm going to store this target address. And now what happens is that the next time I visit the same branch, I already have the target address. So what I'm going to do is I'm going to jump to that address. So no decoding involved. I'm not using any part of my data path yet. The only thing I'm using is just a table, okay? And this is what we call a branch target table. So what happens is that this is all in my fetch state. So everything here is part of the fetch state. In the past, I had my PC reading the address, and we only had this part at the bottom. So we only in the past we only had this, right? So the PC just goes directly to the instruction memory and read the 32-bit here, right? That was what we had before. And now what we are adding is this additional path in this direction, which the same PC address is now used to read another table, another memory, in another sequence of tables, that what it does read is the next PC. So the outcome of this is another 32-bit value, but this value is PC, it's not instruction. And we're going to use this value to then decide whether we want to do PC plus 4 or whether we want to jump to that address. And as you can see, the next PC essentially could be this number that we are reading from here. So next cycle, I can basically use whatever I read from here to jump to this address, okay? So this way, I can always read the next PC by just looking at this table, okay? We also talked about what is the size and how many bits. We told you that ideally you want to have a table as big as your instruction memory. In other words, if this is 32-bit, I want to have a memory or BTB that has 2 to the power of 32 entries. Each one would be 32 bits. So this would be basically the size of my BTB. But this is huge, and we cannot afford to have that. So we need to reduce the number of bits to some other number. So maybe I can do 10 bits and do 2 to the power of 10 times 32. This would be kind of roughly equal to 32 kilobits. So I can do something like that in order to reduce this. So now the question becomes that if I do less than 32, and then let's say I just do 10, since this is 32, I need to select 10 bits of that 32. So which 10 bits should I use? And last time I told you that we're going to use the lower bits because we are assuming that we have what we call locality, which means that addresses near each other, PCs near each other, we want to be able to distinguish and differentiate them from each other, okay? So that was kind of the idea of the BTB, okay? So let's talk a little bit more about the BTB and how do we update it. We still haven't talked about who updates the BTB and How do we know that this is a control flow instruction and how to fix that? Okay. So let's answer the first question. So who updates the BTB? Who actually put the instruction inside the BTB? Yes. Uh-huh. So the question, are you asking about this control signal? Yeah, so the question is like where this control signal is coming from. I'm going to actually show you where it's coming from. So for now, there is a control signal. I still haven't described how it works. But yeah, that's a great question. All right. So the way that we're going to update the table is the following. We know that this is a branch instruction for sure when we decode the instruction. We also know the target address of the branch also in the decode section, decode stage, right? We already showed you how to calculate the target address in the decode stage. So what we are doing is that we're gonna update the BTB during the decode stage, okay? So who updates the BTB, who puts the new instruction into the BTB, or who updates or override the BTB, that will be the decode stage, okay? So decode stage, when it sees that this is a branch, it will issue a control signal to the BTB and provides the PC and the target address to the BTB. So going back to design here, in the decode stage, there will be some signal that I'm not showing here, but this would be a pipeline register. And then during the decode stage, where you have the controller and you have the PC plus offset thing here, you had an adder here, if you remember, that takes the PC and the immediate. So what we're going to do is that we're going to issue two signals. One is like a write signal, and then this one is the target address. And of course, we already have the PC as well. So we send these three signals, the target address, the PC, and the write, and we're going to update the corresponding entry in the BTB based on this. And we only update the table when we see a branch. So when we see an add or a subtract, an R-type or a load or word, we don't need to update the BTB. We only update the BTB when we see a branch, and when we calculate the target address, then we're going to update our BTB based on these three values. How do we make sure that it's only written when it's a branch? We're going to use this control signals to kind of control that. Okay? So that's the first question. The second question is, how do we know that this is a control flow signal? So, so we're going to do this based on this fact that we only update the BTB when there is a branch instruction. Okay? In other words, we are guaranteeing the fact that every entry in the table is corresponding to one branch instructions, okay? If I see an add or a load or a store, I'm not going to put the target address of those into the BTB because there is no target address. So in other words, when I see a match between my PC and the entry in the BTB, then it's at least it's guaranteed that this is pointing to a branch, a previous branch that I've seen in the system. Whether or not this is a correct branch, that's a separate story, but at least I know that this is corresponding to a previous branch. So essentially the idea that how do we know that this should be used is based on this fact that when we are updating this table, we update it correctly. Okay, we only update it with branches. Okay? So quick recap of things that we are trying to do. If you remember, I told you that for branch prediction, there are two things that we are worried about. We are worried about miss penalty, and we are worried about miss rate. Miss penalty, we reduce it to one cycle by bringing the kind of knowing the outcome of the branch to the decode stage. So in that case, even if we are wrong, we are only wrong by one cycle, okay? Then we start talking about miss rate, and we said that, okay, instead of always not taken, let's do always taken for the branches. And that will immediately increase my accuracy from 30% to the opposite of 30%, like 70%. But we said that we need next PC in the fetch, and we use BTB to fix that problem, okay? So now what we have is that we have a system that can predict taken, and if it's wrong, it can fix it in one cycle. Okay, that's what we're gonna have in our systems. And how accurate is this? This is 70% accurate, because on average 70% of my branches are taken. Okay. And then if I want to break this down for you, you will see that essentially we're gonna have two big categories of instructions. So lots of instructions are not branch. So this is R type or I type or U type and so on instructions. For these instructions, as you can see, since my BTB is not gonna have a match, we're already gonna predict not taken for them, right? Because there's not going to be a match in the table, most likely. So that's great. For the branch, then we have two groups, so two categories. For seen before categories, we're going to predict taken because there is a match in the BTB. For not seen before branches, the first time that I visit a branch, we're still going to predict not taken because it's not going to be inside my BTB. So essentially, I have three different options. Either I see an instruction and this is not a branch. Since it's not a branch, it's probably not going to be on that table, which means that I'm going to predict not taken and just move with my PC+4. That's great. Then I'm going to see a branch. There are two possibilities for a branch. Either this branch has been observed before, or this branch is the first time that we are seeing this branch. If this is the first time that we are seeing the branch, since there is no entry that is matching this branch in the BTB, we're going to still predict not taken. This might be wrong, but that's okay. As I said, we don't have 100% accuracy. We only have 70% accuracy. And I already told you the mechanisms for fixing this, right? In the decode stage, we can check the target address and see if the branch is taken or not taken and what we did. So we can always flush things, okay? But then if this branch has been seen before, then it means that there is an entry, hopefully, in the BTB. So we can predict taken for this branch. Again, this doesn't mean that this branch will be always taken, right? In reality, the branch might be not taken. That will also result in inaccuracy. But again, we are saying that there's 70% of the time on average that we're going to be accurate. Okay? Any questions? Yes. So the question is about, there will be cases that you've not seen the branch, but you never revisit the branch again, right? Yes, it's possible. And then in those cases, it's probably you're not going to predict taken. And if those branches are taken, then you are incorrect. So that will be part of that 30%. The reality, if you're asking like on average, we usually have what we call locality. So we're going to have what we call both temporal and spatial locality, which means that most of your code is very likely that you see it again. Okay? So let me actually explain this. So there are two types of locality that you see very often in computer architecture. There's one called spatial locality, and the other one is called temporal locality. So what do they mean? Temporal locality means that if I did something, it's quite likely that I redo it again in near future. Example of this is a loop, right? So if I run a bunch of instructions and this is part of a loop, I'm going to run this again and again and again and again. Or think about a function. If I call a function and run a function, it's very likely that at some point that I return to the normal program, I call this again and again and again. So this is what we call a temporal locality. Interesting thing about program is that there are lots of studies that shows that 95% of your time is only spent on about 5% of your code, which means that most of your code is some form of a loop. Is it a for loop or a while loop? You rarely have like a straight line code that you never revisit. there's always some code that you come back and again to revisit. And again, you can, next time that you're writing a code, pay attention to your code, how much time you're spending in a loop, and you'll see that it's actually quite a lot. Which means that it's very, very likely, back to the question that's been just asked, that how often it is that we don't see a branch, and the answer to that is it's very, very rare, because we always kind of come back to it. So this is what we call temporal locality. There is also what we call spatial locality. It means that if I use something, it is very, very likely that I'm going to use the surrounding of that. By surrounding, I mean surrounding addresses. Again, for instruction, this means that if I run this instruction at PC equal to X, it's very likely that I'm going to run things after or before it as well. So around PC plus 4 or PC plus some number, and this number is small. Okay. The same thing applies to data, and you will see caching later in the course. When we were talking about caching, you will see that if I'm accessing a content from an array, it's very likely that I'm going to access other components in the same array, right? So you're rarely going to see that, oh, I only use A1 and I never use A2 or A3 or A4 and so on and so forth. So this means that this will give us the idea that I'm going to later talk about, is that if I bring A1, maybe it's a good idea that I also bring A2 and A3, because in future I'm going to use them. This is what we call spatial locality. And the reason that we are, for example, using the lower bits of PC is trying to optimize and use this locality. Okay? So this principle of locality is very, very common in our languages. Regardless of which language you're using, you're going to use some form of this locality in your systems. As I said, programs are very predictable. This is a stat. I said 95% was wrong. 90% of time is only spent on 10% of the code, which means that most of your code is just used. It's not going to be used unless most of your time is going to be spent on a very, very small portion of your code. Okay? So this is how we're going to then design our BTB. As I said, we take the PC, okay, and we're going to use the portion of the PC to indexing in this BTB. How many bits do we use? We use n bits depending on how many entries we have. And as you can see, I'm going to use the lower bits of PC because I want to use spatial locality. Another thing that you need to pay attention to is that I'm not going to use the first 2 bits. Why? Because I'm always assuming that I do PC plus 4, PC plus 4. The first 2 bits is not going to be used. Again, if I assuming that all of my instructions are 32, then I don't need to use either of these 2. If I assume that I sometimes need 16, then I need to use, I need to discard the first, but I need to keep the second. For now on, to make things simple, I always assume that everything is 32. That's why I'm going to get rid of the first 2 bits, because first 2 bits is going to be always 0. There's no point of keeping that. There's no information there. So I just start from bits number 2 and then use n bits from there. Okay? And then here's what we're going to do. So as I said, entry in this BTB is going to be a PC address. It's going to be a target address, which is a 32-bit. We're going to feed this into this mux, as I said, and this is connected to your PC. So your 0 would be PC plus 4. And whatever you read from here would be the second content, which would be PC plus offset, or the target address. I still haven't talked about how do we select the controller, but this would be kind of like the logic behind this, okay? So now the question is, how do we compare the PCs? In other words, how do we decide the matching? For matching, we need to have some form of an ID, right? So this PC comes, we need to compare this PC with some tag or some ID here, okay? So what do we do that? We store a tag, a unique ID for each instruction. Remember, I told you that we're going to use the address itself as the tag, because the address itself basically reveals information. There's a one-to-one mapping between the address and the target address, right? So we're going to use that as a tag. So the way that we're gonna use is we're gonna have a table like this that the table gonna have two entries instead of one. They're gonna be the tag and they're going to be the address. So this is your target address. This would be the tag, which is itself is the PC that is corresponding to that branch, okay? So this would be 32-bit. This is also 32-bit. And the number of entries, depending on how many entries you have, that would be the n bits that you have. So based on this tag, here's how it works. So I'm going to take the current PC, okay? And then I'm going to compare my current PC with the tag that I have here, which is the PC of that target address. If these two PCs matches, it means that this was the branch that I've seen before. So this means that now we have a match. And I'm going to then connect this to that multiplexer that we had. So the controller for that multiplexer is basically this comparison. If this is a match, then I need to select this address. If these two are not matching, then I'm going to select this. Okay? So one more time. So I have some instructions, and at some point, let's say as PC equal to 100, I have something like branch equal x2, x1, and some label. Okay? And I have some bunch of other instructions. Let's say at PC equal to 200, I have another branch, BQ, X3, X1, label 2 maybe, okay? So I have a bunch of branches in my program. There could be many, many branches, okay? So here's what happens. So I start executing this. So for every one I check BTB, nothing happens. Then I reach to this instruction, and I still haven't seen this instruction before. So my BTB is still empty. Okay, my BTB is still empty at this point. But then this instruction goes to the decode stage, and we see that, oh, this is a branch. So what we're going to do is that we're going to update our BTB with what? With 100 as my tag and label as my address. So the entry in my table going to be like this, okay? And this would be my tag, and this would be my target address, okay? I'm going to save the entire PC as my tag. Then I'm going to continue, and then I'm going to reach to this instruction, and then again, this is a new instruction, same story. I'm going to store 200 and label 2 here, okay? And as I told you, the idea is that at some point I'm going to come back, okay? And for example, let's say I come back somewhere here. And then for each of these instructions, I'm going to check my, my BTB and see that tag doesn't match. But then I'll reach to this and see that, okay, the tag of the current PC, which is equal to 100, matches with this number. And this is what I'm showing you here. The value that is stored here, which is 100, is equal to the PC that I have here, which means that now this is a match, which means that instead of getting PC plus 4, now I'm storing whatever value is stored here. In this case, the value would be label. So in other words, my next PC would be equal to label. And then I'm going to continue this way over and over again. All right? Yeah, question? Yeah. Yeah, so the question is, does that mean that you are you're having a connection between your decode and fetch? Yes. We had it before as well. Remember that we had PC plus offset going all the way back to the PC? That's the same wire. Yes. If it's not in the BTB, you predict not taken. Yes. Yes. So the question is, if I see, so this applies to all the instructions. Remember, we always read BTB. Okay. So all these instructions gonna check this, and for all of them would be not match. Okay. So in other words, for every single PC, we're gonna read something here and see that there is no match, and then we're gonna always predict. We're gonna always take 0, which is PC plus 4. In other words, we're gonna predict nothing. For newer branches, same story. For not seen before branches, since still there is no match, we're gonna predict not taken. But if we see the branch, then we're gonna predict take. Yes. So the question is, what will happen when we solve the branch again? Yeah. So we go first time this way, and then we put things in the BTB, right? And then at some point, let's say there is a JAL that jumps back to here, okay? So then we start executing this again, and then at some point, we're going to reach to this instruction here. We see that PC is equal to 100, and we're going to see that we also have a tag that is also equal to 100. So which means that the PC that is coming from the instruction and the PC that we have stored in my tag, they are the same. So this is the value that I've stored here is 100. The current PC is also 100. So I see 100 here, I see 100 here. Then this will be equal to 1. So then it means that I'm going to select this. What I have stored here, this is label. So I'm going to, basically my next PC will be equal to label. And the same story for 200, right? So again, when I get to this point, I'll see that my PC now is equal to 200. And somewhere else in that table, I have stored that 200. And again, I'll see 200, 200, 1, 1. And then this way, I'm going to select label 2. Yeah. Uh-huh. So the question is, when we are checking the non-BTB instructions, do they get entry in the BTB? And remember, I told you that who updates the BTB is decode. Okay? So who updates or who creates entries in BTB is the decode stage. Decode stage only creates an entry in BTB if this is a branch instruction. Because we already decoded that instruction, we know that this is a branch instruction, we know the target address, so we only write to BTB when this is a branch instruction. If it's an add instruction, we ignore, we just continue. So we never create an entry for non-branch instructions. So yeah, so what will happen is that every instruction will get checked, but since the tag is not stored in the BTB, it will not be a match. If it's not a match, what happens is if this is not equal to 0, if it's not equal to 1, we will select PC plus 4, and that's exactly what you want to select. Good? Yeah. Yes. So the question is, since this is less, so first of all, if I store the entire PC, okay, if I store the tag is the entire PC, then there will be no collision at all because there is a one-to-one mapping between branches and PCs. There is no instruction that has the same, for every single instruction, there is a unique PC. So there is no collision at all, okay? In other words, if I predict things inside the BTB, it is guaranteed that this is indeed a branch instruction, okay? That's it. But now the question is, if my tag is less than PC, then there is an opportunity for collision between instructions. So for example, if I go back to the example that I had, I told you that PC is equal to 100, okay? But let's say, for example, I have another PC that is equal to, let's say, 20200. And let's say I only store these lower bits, this lower, like each one is 4, let's say lower 12 bits, okay? So in that case, if this is 10, 00, 30, all of these map to the same entry in the table, which means that I think that I've seen this branch before, but either this is not a branch at all, or we thought that this is a different branch. So it could be also collision between branches. So in those cases, we accidentally predict taken, and our next PC would be label 2 or whatever it is, but in fact it should have been PC plus 4. This is similar to the case that this we predict taken and indeed it should have been not taken. So we have a mechanism in decode stage again that we see that either this is a branch that was supposed to be not taken and we predict taken, or this is not a branch at all and there was like an accidental collision. In both cases, this will result in what we call a misprediction, which we need to replace it with the bubble. So we already have that mechanism. So they all goes into that 30% of the time that we mispredict. Yes? Correct. So now so for now, the question is we are assuming that the tag table is storing the full 32-bit, yes, which means that there is zero possibility for collision. But still there is a possibility for misprediction because if I seen this branch before, last time I saw it, the branch was taken, but it's not guaranteed that this time the branch will also take. Okay? But yeah, so we kind of like now getting to the point that we want to optimize this a little bit further. Let's see, I don't want to store the entire 32-bit because this is still very large. There is 32-bit for the tag and there is 32-bit for the branch address. And if I have thousands of these entries, the size is still too big, okay? So how can I optimize this? The first thing I'm going to do is that my first observation is that I don't need to store the entire 32-bit because part of the address is already embedded in the index. What do I mean by that? So if you look at this kind of address model that we have here, you'll see that what I want to store is the entire thing, okay? But I'm already using this part to indexing this table. So in other words, there is a one-to-one mapping between the index and each entry. I don't need to store this anymore. I can just use the index to recreate my address. So here's what I'm going to store. I'm going to store this part as my tag, okay? In order to create the address, I'm going to just compare, I'm going to use this part to address this table, and I'm going to just use this part for the tag part of the comparison. Why? Because I don't, because there is, so for example, if I have 12 bits here, and I have total of 32-bit, and I'm not really using the first 2 bits, so what will happen is that every bit here has a unique mapping in my table. I don't need to change this. I only need to store this part of the address as the tag here. So I'm going to only compare this part and this part together to know whether these two are matches or not, right? So again, the index part of my address is using for indexing the table, and the remaining part is the part that is unique for each VC. That's the part that I'm going to just store. So I'm going to save a little bit here. And as I said, since this lower 2 bits is always 0, 0, I'm not going to use it for anything. I'm not going to use it for indexing. I'm not going to store it for tagging. So what I'm going to store in my tag table is 32 minus the number of bits that I'm used for indexing minus 2 because of the first 2 bits. That's what I'm going to store in my table because I already used the index to actually directly map where it is stored in my table. If this was not one-to-one mapping, which means that my entry could have been any line in this and not a particular line, then I would have had to store the index as well. But since I have one-to-one mapping between the index and the entry, then I don't store that in my tag. Okay? So what I'm changing now is that I make the tag table smaller. It used to be 32, but now I change it to 32 minus index minus 2. Okay? So this at least save a lot of space because for every entry, I have less number of bits. Okay? So for example, if I have 10 bits, I remove 32, so 32 becomes only 20 bits. and 20 times BTB is just a large number that I'm saving. Okay? Make sense? Cool. All right, so here's what is going to happen. Okay. So in my kind of PowerPoint design, I'm going to have this design here, which I'm going to have a BTB, which what it does is it takes the information from the lower from the decode stage for updating and PC, and then it's gonna create a target address and also creates a control signal. This is the match, and this is the target address. And now instead of doing PC plus 4, which I'm having here, I'm gonna have a mux that decide between the address created by BTB or the address created by PC plus 4. And then this way, I always can predict within one cycle what would be the next address in my design. Make sense? Great. All right. So to kind of summarize, we try to answer this where, whether, when question. We try to know the outcome of the branch in the second cycle in the decode. And we also try to predict not taken for the branches that we have seen before. And we use BTB for that. We design our BTB based on using some form of a tag to have one-to-one mapping. For now, as I said, we assume that there is no collision, which means that we always know exactly the entire bits of PC. And then we have this kind of structure where if there is a match, then we're going to change the PC to PC plus offset. If it's not a match, which means that for all the non-branch instructions and for all the non-scene branches, this will be not a match, then we're going to just do regular PC plus 4. Okay? That's kind of the status quo. But let's actually see if we need to do a little bit more. And here I kind of try to categorize different types of branches that we have. So if you look into these branches, you will see that there are some branches that are always taken, like JAL and CAL and so on and so forth. But there are some branches that are not necessarily always taken. So we have what we call conditional branches, and this is like BEQ, BLT, and all those things, that you need to check a condition, and based on the outcome of the condition, the branch may be taken, the branch may not be taken, right? So in other words, the outcome of the branch during the fetch time is unknown because we need to check, read the registers and do some checking. But there's also some other branches that are always taken. And this is our JAL and JAL-R. JAL and JAL-R always taken. There's no conditional branching. And if you remember, we had these pseudo instructions such as call and return, which was also always taken, which was also JAL in some sense, but we had pseudo instructions with them. And then we have indirect branches, which are JAL-R instructions, which depending on the value that's stored in the register, we jump. But again, those are all always taken. But there's also another thing that we need to be worried about, and that is what are the possible outcomes? What are the possible addresses, okay? For conditional branches, we only have two outcomes. We either take the branch, which means that it's PC plus offset, or we don't take the branch, which is PC plus 4. So two possible outcomes. For unconditional branches, there is always one outcome, and that is PC plus offset. For call is also the same. That's the beginning of the function, which is also PC plus offset. For return, however, there are many, many outcomes. Depending on where we are returning from, there are multiple ways that you can return, right? So for example, let's say I have a main function, and then I call a function called foo. And then within foo, I have a bunch of things, and I have return. So where do I return to? I return to here, okay? But then I have another function, let's say, call bar. And bar is here, and then you have a bunch of things, and then return, and return jumps here. So we have a return instruction that could jump back to different places. So there is different addresses for return, which we don't know. Still, it's always taken. There's always one direction, but the outcome of like the where it jumps to could change. So if I see a return, one time this might be called from main, the other time it might be called from bar, it might be called from foo, and the same return could jump to other locations. So just seeing a branch wouldn't be enough for some of these branches, okay? And then same story with indirect branches. The address that we're going to jump to depend on the base address, right? So we're going to jump to whatever this R is plus the offset. And if I update this R, this register, then the address that I'm going to jump to is different. So there are many, many outcomes that depends on the value of the registers, okay? So what I'm trying to say here is there are two things when we are doing the branch prediction and designing our BTB. The first is how many outcomes my branch has. For branch equal, or for what we call conditional branches, such as BEQ and BLT and so on, there are two possible outcomes. Sometimes it's taken, sometimes it's not taken. So we need to figure that out. But there are two different outcomes. It's either PC+4 or the label. There's no other outcome. For JAL instructions, it's great. One outcome and one possibility. That's the dream scenario here. Same story for calls. So these are the easiest ones that we can treat. But then we have return and indirect branches, which unfortunately they're always jumped, they always taken, but the address may not be the same address that we think. Okay? So if you look into the BTB and where BTB could be helpful, you will see that depending on the type of branch, BTB could fix the issue or could not be helpful at all, okay? So let's actually look at it. So for R type, for non-branch type instructions, for R type, I type, LW, SW, and all those things, since BTB won't match, because remember, we never create an entry for those instructions, PCB won't be matched, and PC will be always PC+4. So this is great. So BTB is great for non-branch instructions. For JAL, it's also PC always will be taken and will be PC plus offset. And that's also great. It's a match. Usually, for the first time we see the JAL, you're going to put it into the BTB. The next time we see the JAL, we see that this is a match, and we're going to have the address. And this address is 100% correct. That's the important thing, because there is always one outcome, and that outcome is always taken. So which means that our BTB performed exceptionally well with my JAL instruction, except the first time that we don't predict. Afterwards, we always hit 100% on JALs. For BEQ, it's iffy. If the branch is taken, then BTB is going to help us, because we're going to always predict taken, right? So if the branch is indeed going to be taken, like the condition is true, and we predict taken, then we are good. If we predict taken, but the branch equal is not, the condition is not true, then we have what we call a misprediction. So BTB kind of helps with branch equal or generally conditional branches, but not all the time. And lastly, for things like JALR and return, actually call is not part of this. Call is okay. For return and JALR, since the outcome of the branch is always taken, but the address that it jumps to might differ from one to another, BTB also may not be helpful. It may be helpful in some cases, but it may not be helpful in other cases, okay? So to summarize, BTB is not going to answer all the problems that we have. In some cases, it's going to be useful. In some cases, it's not going to be useful at all. And in some other cases that it may or may not be useful, okay? So that's kind of like what I want you to know. Any questions here? Okay, so what we can do to further improve this, we're going to focus on this one, okay? So we see that branch is kind of helpful, but since the outcome of the branch is sometimes taken and sometimes not taken, maybe there is an opportunity to further optimize this. Instead of rigidly always predicting taken or not taken, maybe we can somehow predict the correct outcome. Now that we have the capability of predicting taken or not taken at our will, maybe it's time for us to now make this decision dynamically, okay? So as I said, for conditional branches, we are doing 70% accurate, but unfortunately, we are missing 30% of the time, okay? So now the question is, can we do better? And this is what we call a branch predictor. So branch predictor is this additional logic that we add to our kind of BTB logic such that it can decide based on some factor that I'm going to explain whether or not this branch is going to be taken or not. So we're not going to just rely on whether there is a match in BTB or not. We're going to also query another logic, which we call branch predictor. And branch predictor going to tell us whether we think this branch is going to be taken or not. Okay? So we're going to check two conditions. One is if there is a match, and if it's a match, whether it's a good idea to take this branch or not. And again, why this is helpful? This is helpful for those conditional branches, because conditional branches is not just if I've seen this before, I'm going to do the same thing. Sometimes it's going to be taken, sometimes it's not going to be taken. So think about if then else's, for example, right? So if you have like something like an if then else, you will see that depending on the condition, sometimes the if is taken, sometimes this else is taken. So how do I know which one? What I'm going to do is that, again, I'm going to use history, but I'm going to use like a little bit longer history. So I'm going to see the previous outcomes of a particular branch to make a decision about that branch, okay? So what people, again, have seen is that if a branch has done something, it's very, very likely that it's keep repeating that thing over and over again. Think about, for example, backward branches, like something like a loop that goes back. If it's a condition, right? So it's still like branch equals something something, and then label. But if it's a loop, more often than not, this branch will be taken, right? So most of the time, your loop's gonna be taken and you're gonna repeat, and only one time it's gonna leave the loop, right? So what we're going to do is that we're gonna have a mechanism for tracking the behavior of the branch, and we're gonna incorporate that into our prediction, okay? So here's what we're going to do. We're gonna add this additional 1 bit. So think about this as one extra column that we are adding to our BTB, and we call that branch history table, or BHT, okay? So we're going to do exactly the same thing that we were doing before. We're going to take the PC and index it to the table. We're going to check the tag, and we're going to see if it's a match or not. If it is a match, then we're going to have an additional condition. This condition is just 1 bit, okay? 1 bit for now. And that 1 bit is the behavior of the branch previously, okay? Last time I see this branch, I'm going to store if the branch was taken. I'm going to store 0 if the branch was not taken, okay? And I'm going to store that number into this column, okay? So what I'm going to do is that I'm going to read that number and end it with this number. If this is 1 and this is 1, this will be 1, which means that now we should take the branch. But if either of these two are not equal to 1, it means that we shouldn't take the branch, okay? So what we are doing now here is that we're not just relying on the fact that this is a match. We're also going to additionally consider what was the last time this branch has been seen? If it was taken, it's highly, highly likely that it's taken again. If it wasn't taken, then it's also like highly likely that it's not going to be taken again this time. So we're going to predict not taken. So even if we store it, we're not going to be predicting taken. And what you can see here is that for things like JAL, okay, that is always taken, what we're going to store here is 1, which means that whenever I see a JAL, I also store 1, so nothing bad happens. So I'm not going to impact my always taken branches. But the beauty is when I see a branch equal, if the last time it was not taken, then I'm going to store 0 here. If the last time it was 1 here, then I'm going to store 1 here. So I kind of like bias my outcome of my branch based on the previous outcome of the branch. And the idea and the reason that this will work is that programs tend to repeat their behaviors, okay? So the underlying reason for this to work is that branches tend to repeat their behavior. If they've been not taken, most likely they're going to be not taken. But again, remember, these are all predictions, okay? It doesn't mean that they're 100% true all the time. There could be that we think that this is not taken, but it's in fact taken, or other way around. That's okay. We can always go back and fix it. Okay? Yes. Great question. So if my branch is kind of toggling, then this is horrible, right? So it's one step behind of the actual. Again, so this is just algorithms that we can do to optimize this, okay? And in fact, that's what we're going to do just now. But the idea here is that you can predict taken, not taken, based on just the previous 1 bit. But you can say that, oh, I don't want 1 bit, I want 4 bit. You can also do that. There's also other ways that I'm going to describe how you can do that. Any other questions? Great. So as you can see, for all control flow instructions, except conditional branches, this will be equal to 1. So again, for all the always taken branches, there is no need to make this 0. There's always can be this can be equal to 1. Only for conditional branches that are sometimes taken and not taken, we will change this. And again, who will check this and who will update this? The same entity that updates these, that is the DE. So during the decode stage, we already know the outcome of the branch. Remember, we know the condition and whether or not those values were correct. What we can do is that we can use that number to update this value here as well, okay? So during the decode stage, we know whether or not this is a branch. You know, the weather question. And then we know where it's going to jump. Sorry, the weather question is whether it's taken or not, right? Taken or not taken. We know that during the decode stage because we compare the registers, and that would be this bit here. We know where it jumps to by computing the PC plus offset, and this is what we're going to do here. And we know that when it's branch or not, whether this is a branch equal or not, or whether this is, for example, an add. And this is what we're going to do here. So we're going to update the tag table based on that. Okay? So all of these things happen during the decode. The code will update this BTB during that cycle. All right? Questions? Great. Let's have a quick break. We're going to come back and finish this.